Everyone. Today we'll be presenting our analysis and design on for sustainable waste management in soy milk production. So I'm Venting and I'll begin with an overview of the production process. So in a typical soy milk production line, the process begins with the cleaning of the raw dry soybean by dehulling the shell and boiling it to soften it, followed by grinding to extract the protein-rich soy milk, producing the soy milk slurry. The mixture is then steamed at high temperature to kill off any bacteria and is filtered through centrifuge to separate the okara and the soy milk. The extracted soy milk is then mixed with additives such as sugar, vanilla extract, or minerals to enhance the taste. It then goes through homogenization to break down large fat globules and protein clusters into smaller, more uniform particles. This results in a more stable emulsion, preventing separation and settling, and enhancing the overall quality of the soy milk. Homogenization also improves the taste, mouthfeel, and appearance of the soy milk. It then goes through pasteurization to kill bacteria again, and is eventually cooled for packaging. So throughout this process, okara from the centrifuge are generated, such as okara from the centrifuge, soybean hull from the cleaning step, and the wastewater from the boiling and grinder. So on average, 1 kg of soybean produces 2 kg of okara, 80 grams of hull, and 10 kg of wastewater. Moving on, I'll give it to Roy.
Go. My section focuses on the environmental impact of the waste produced in soy-based food processing. First, okara, the soy pulp left over from making soy milk has very high BOD and COD. When dumped into rivers or landfills, it consumes oxygen, killing fish and disrupting ecosystems. In landfills, it releases methane, a potent greenhouse gas. Okara is also hard to manage because it spoils quickly, usually within 1 to 2 days. If stored improperly, it creates runoff that causes eutrophication or excessive algae growth in water. Then we have soybean hulls. They're generated in large amounts, and when they decompose without oxygen, they emit both methane and carbon dioxide. Rainfall on hull creates leachate that can pollute waterways with nitrogen. Stored hulls also smell bad, attract microbes, and are often discarded even though they could be reused as animal feed, compost, or even biofuel. The wastewater from soy processing is another problem. It's rich in organic matter, which raises the biochemical oxygen demand. When discharged untreated, it depletes oxygen in water, harms aquatic life, and contributes to algae blooms. It also clogs pipes and damages treatment systems. Finally, the industry also produces CO2, which worsens global warming and contributes to ocean acidification. Altogether, these poses serious environmental risks and highlight the need for better waste management.
Hello, now I'm Zafri and I'm going to explore some of the waste management issues and challenges for soybean production. Okay, so what are basically the issues? So we have high volume of organic waste, which is okara, wastewater management challenges, and also regulatory issues. And now we're going to talk one by one about all the aspects. So first of all, high volume of organic waste, which is okara. So soy milk production generates a significant amount of okara, which is the fibrous byproduct left after soybeans are processed. For every kilogram of soy milk produced, around up to 1.2 kilograms of okara is created. Okara is about 80% water, which is high in moisture. That's why it is perishable, difficult to store or transport, and also prone to microbial spoilage and foul odor. So okara often discarded and also landfill despite its potential such as animal feed, compost, and even food ingredient. So what are the issues? So the main challenge here is the lack of infrastructure or incentives to turn okara into valuable products. That's why it leads to wasted resources and environmental pollutions. Okay. So wastewater management challenges. So another major issue is wastewater. During soy milk production, water is used for soaking, grinding, and cleaning. This wastewater contains high levels of organic matter, proteins, fats, and suspended solids with slightly acidic pH. So what's the risk basically? The small and medium-sized producers often discharge this wastewater untreated, causing water pollution, oxygen depletion in rivers, and also eutrophication. So, for regulatory issues, we have four, which is inadequate enforcement of wastewater discharge limits, lack of specific regulations for agro-food byproducts, economic barriers to compliance, and also lack of incentives for waste valorization. So, firstly, inadequate enforcement. While many countries have environmental regulations, enforcement is often weak, especially in developing regions. Regulatory bodies may lack resources or political support, so violations go unpunished. As a result, untreated wastewater is frequently discharged into the environment, harming aquatic life, human health, and soil quantity. Okay, so lack of specific regulations for agro-food byproducts. Briefly said, there's also a legal area when it comes to byproducts like okara. Is it food waste, agriculture, biomass, or animal feed? Without clear classification, there are no mandatory standards for safe disposal or reuse, and no monitoring of how much is produced or where it goes. This leads to an inconsistent handling and missed opportunities for resource recovery. So next is economic barrier to compliance. Even when regulations exist, many small and medium-sized producers struggle to comply due to high costs. Installing treatment systems or composting facilities requires significant investment, which is often out of reach without government support or access to credit. And lastly, lack of incentives for waste valorization. Finally, there's a critical lack of incentives to turn waste into value. Unlike other sectors, the plant-based food industry rarely receives subsidies or tax breaks for composting, biogas production, or innovative uses of byproducts like okara. Without policy-driven support, most producers default to landfilling or dumping, missing out on circular economy opportunities.
Moving on to the compliance with industrial wastewater regulations. In soy milk production, wastewater contains a high organic load of soluble proteins, fats, fibers, and sugar, making it the most environmentally damaging waste stream. If untreated, it poses serious risk to water bodies, aquatic life, and public health. To tackle this, Malaysia enforces the Environmental Quality Regulations 2009 under the Environmental Quality Act 1974, which governs industrial wastewater discharge. Soy milk manufacturers are legally required to install and operate wastewater treatment systems such as sedimentation and biological treatment, and they also need to regularly monitor effluent quality. Before releasing wastewater, the effluent must meet strict limits, including BOD at or below 50 mg per liter, COD at or below 200 mg per liter, and TSS not exceeding 100 mg per liter. As for the pH, it should range between 5.5 and 9.0. Compliance with this standard is essential to protect the environment and public health. In Malaysia, the Environmental Quality Industrial Effluent Regulations 2009 under the Environmental Quality Act 1974 require all soy milk manufacturers to install wastewater treatment systems and comply with strict effluent discharge standard. Wastewater discharge directly into rivers must meet standard A, which enforces stricter limits, while discharge into municipal sewer systems must comply with standard B. Non-compliance can result in around 100,000 fine or 5 years jail, closure orders, and it can also cause serious environmental damage, such as fish kills and algae bloom. Unlike wastewater, solid byproducts from soy milk production like okara and soybean hull faces a major regulatory gap in Malaysia. Existing laws, including the Environmental Quality Act 1974 and Food Act 1983, do not really define how these agro-industrial residues should be classified or managed. They are also not listed as hazardous casual waste, nor are they clearly categorized as agricultural waste, and they also fall outside mandatory food waste recycling rules. As a result, okara and hulls are often dumped in landfills or open fields. There are no official standards for hygienic handling, storage, and transport to convert these byproducts into valuable resources. Addressing this gap is crucial to promote sustainable management and to support circular economy efforts in Malaysia's agro-food industry. Malaysia can look to successful models like Japan and South Korea, which have robust policy promoting the reuse of okara in food, animal feed, and biogas. These countries offer financial incentives for composting and bioconversion, alongside enforcing strict sorting and recycling laws, ensuring food industry byproducts are not wasted. For Malaysia to align with circular economy goals, several key actions are needed. Firstly is to classify okara and soybean hulls as organic industrial byproducts to remove legal ambiguity. Secondly, the Department of Environment and Ministry of Agriculture should develop specific waste handling guidelines. Lastly, Malaysia should incentivize reuse and learning from Japan's feed-in tariffs, as well as South Korea's funding for biogas plants.
To the waste treatment design. So to recap, soy milk production generate not just nutritious beverage, but also significant amount of wastewater. So and solid byproduct like okara and soybean hull. So these waste streams are rich in soluble protein, fat, carbohydrate, and fiber, which results in high amount of BOD and COD if discharged untreated. To address this, we designed an integrated waste treatment system that incorporates both physiochemical and biological process. We have strong focus on the resource recovery and environmental sustainability. So on average, 3,000 kg of soybeans is used per day in a large farm. So based on the amount of waste produced per kg of soybean used on the previous slides, from the production line, 30,000 kg of wastewater is discharged into a holding tank, while solid byproducts like 6,000 kg of okara and 240 kg of soybean hull are collected through sieves and filter into a separate solid hopper. We will now go to pre-treatment. So the wastewater first undergoes screening to remove large particles such as floating pulp or fiber fragment. This is important because to prevent the clogging of pumps, equipment wear, and reduce digestion performance. On average, 2% of total wastewater mass has removable solid. So from the 30,000 kg of wastewater, 600 kg of solid will be screened, and it will be added into the grinder along with the okara and hull. So at the same time, the 6,840 kg of okara and hull from the screen solid and from the hopper is sent through a grinder to be shredded to increase the surface area. This improves the breakdown during the biological treatment. So all the materials are blended into a total of 30,600, 240 kg of uniform slurry in a mixing tank. So this slurry then enters the anaerobic digestion reactor. Normally, it will be a CSTR or continuous stirred tank reactor, operating normally at mesophilic degree of 35 to 37 or a thermophilic degree of 55 degrees Celsius temperature for a period of between 15 to 25 days. So here, organic matter is converted by microbes into biogas and digestate. So we'll explain this process in the CSTR first. So in the CSTR, we have total of 6,840 kg of total solid. From research, volatile solid is made out of 80% of total solid. So we will have 5,472 kg of volatile solid, and only 50% is converted to biogas. So 2,736 kg of biogas is produced in the CSTR. So normally the biogas yield is 0.6 meter cube per kg in the CSTR. So it will produce about 1,641.6 biogas per day. So the biogas typically contains only 60% of methane. So there will be about 984.96 amount of methane in the biogas. So a cubic meter of methane approximately contains 10 kilowatt per hour of energy. So every day it will produce about 9,849.6 kilowatt hour per meter cube amount of energy. The remaining 2,736 kg of volatile solid that is now converted to biogas is going to be further processed with the slurry to form the digestate. So the biogas is captured in a storage tank and can be used in multiple ways, such as heating for boilers within the factory, or to generate electricity via combined heat and power units, or it can be upgraded into biomethane as a renewable fuel source. The remaining digestate is not wasted. The liquid portion can be applied directly as a biofertilizer since it contains plant valuable nutrients like nitrogen, phosphorus, and potassium. The solid fraction can be further composed to create a stable, odorless compost, supporting soil health and reducing dependency on synthetic.
Why you can't instantly discharge wastewater after anaerobic digestion? Many assume that wastewater is safe for discharge, but that's not the case. One major reason is the high levels of residue organic matter, particularly COD and BOD. AD typically removes only about 50 to 70% of COD, which means volatile fatty acids, sugars, and proteins remain in the effluent. As a result, the post-treatment COD can reach up to 20,000 milligrams per liter, and BOD levels may still be as high as 7,000 milligrams per liter. To put that into perspective, Malaysia's Department of Environment under Standard B sets the legal discharge limits at just 200 milligram per liter for COD and 50 milligram per liter for BOD. So clearly, this effluent is far from acceptable for release. Another critical issue is pathogen survival. AD does not fully eliminate pathogens or coliforms. If you release this untreated effluent into water bodies or use it for agricultural irrigation, it can pose serious health risks both to aquatic ecosystems and to humans, especially if it contaminates crops or drinking water sources. Last but not least, we need to talk about nutrients, especially ammonia. During AD, during anaerobic digestion, the breakdown of proteins releases large amounts of ammonia and nitrogen. Typical concentrations after AD can range from 500 to 1,500 milligrams per liter, while the legal limit under DOE standard B is just 10 to 20 milligrams per liter. If this is discharged untreated, it leads to eutrophication, where excess nutrients cause algae blooms, depleting oxygen in the water and harming aquatic life. To deal with this, aerobic post-treatment like nitrification is required to bring ammonia down to safe levels.
Okay, so now we're going to talk about the post-treatment. So based on previous slides, in our project, we designed a wastewater treatment system that ensures the effluent meets environmental discharge or reuse standards. This is especially important for agro-industrial residues like okara and soy milk wastewater, which produce high-strength waste streams. Okay, so to achieve this, we incorporated a combined aeration tank and membrane bioreactor (MBR) system as our post-treatment design. Okay, so that's why we need to further treat the digested liquid in order to meet the strict discharge or water use standards, such as BOD less than 20 milligram per liter and COD lower than 200 milligram per liter. Okay, so now what we'll cover. So first we are going to cover about the aeration tank and also membrane bioreactor (MBR). So for aeration tank, the aeration tank is the biological heart of our system. It pumps oxygen into the wastewater, promoting microbial activity. These microbes break down remaining organics and convert ammonia to nitrate through nitrification. This step typically removes 60 to 90% of BOD and prepares the water for membrane filtration. Okay. Next, we use a membrane bioreactor or MBR. This advanced unit uses ultrafiltration or microfiltration membranes to physically separate clean water from the biomass and suspended solids. It can remove around 95 to 99% of BOD, 90 to 98% of COD, and TSS to below 1 milligram per liter, and also pathogens by approximately 99%. Our system produces about 3,624 kilogram per day for treated water output, and BOD around less than 10 milligram per liter, COD 50 to 100 milligram per liter, TSS less than 1 milligram per liter, and also pathogen, which is 99% removed.
Waste treatment in soy milk production, which is to turn byproducts, okara, hulls, and wastewater into valuable resources. As you can see here, this is the flow diagram that illustrates an integrated waste management solution for soy milk production in Malaysia. The process begins with the waste input, which is the high organic load wastewater that is treated to anaerobic digestion, which breaks down about 50% of volatile solids to generate renewable biogas energy. The remaining digestate undergoes solid liquid separation, and the liquid fractions further purified using a membrane bioreactor (MBR) system, and then it produces clean recycled water which is suitable for reuse, and the solid residue is processed into organic fertilizer, and lastly it closes the resource loop. As you can see here, this is the environmental and operation benefits, which is the biogas use, water reuse, and digested solids, as well as the other benefits. Overall, the system embodies a closed loop and low waste approach that is aligned with the principles of sustainable development and industrial ecology. Thank you.